So this demo will show you how to log into Young, how to test that your job has sufficient memory, and how to adjust the memory used in the job. So first things first, I have an alias set up on my computer where if I type Young, it will log me in. To see what this is, we'll just do type Young, and you can see I'm using SSH with X forwarding. This is my username @Young. You can put this in your bash script if you haven't already. So this logs me into Young. You get your usual logon screen here. Okay, so first things first, the job memory tests are in mem test, and we're looking at a script called run mem test. Now I'm using Fortran. This equally could have been done in C++ or another language. I chose Fortran just because it's arguably the most common language if people are writing their own code, and it also just, I think, has slightly more transparent memory allocation. Okay, so the code works as follows. You have a use MPI, so we're using message passing interface for this particular example. Message passing interface essentially creates a range of different processes depending on the choice in the run script, and these range of different processes will essentially all run the same code. So everything after MPI initialize you can think of being run on however many processes you specify. In this example we're going to just do a single node, so that's 40 processes. Notice we could have gone to 80 with the hyperthreading. In my experience for MPI jobs, generally using one process per physical core tends to work better, but your own experience might be different, so definitely try this out. Okay, so the initialize and finalize basically just tell it to run this code on the 40 cores that we're talking about. And we're specifying a variable size n, which is just under 4 gigabytes. So that's 3.999 times 1024 cubed. So that goes from kilobytes to megabytes to gigabytes. So we're saying we want 3 gigabytes of data divided by A. Now A is the size of a single variable. So the number of variables we want is basically going to be 1/8 of the actual memory size. So it's 8 bytes essentially per variable. And this is because they're double precision variables. If you're using single precision, then your variable size will be 4. Then we simply just allocate an array of this size, and then the program is essentially just doing nothing interesting. It's just looping through, and then looping through each element of the array and just setting a random number. So the idea of this is just to give the program some work to do, which will allow us to profile it. And the thing we're interested in is this basically allocating of this array, and just checking how big that is for a given node. Okay, so that's the entire purpose of this code. It's worth noting, by the way, just if you're going to test these things out yourself, unless you actually use the array, then the optimizing compiler often avoids actually allocating things. So if you're not actually specifying every value of the array, then it will start to do some clever things where you'll notice memory use might be slightly different. Okay, so I'm doing this with VI, so I just write and then quit. And then in order to compile this, I use the Intel Fortran compiler, or the default Fortran compiler. I'm compiling it just to a.out, which is the variable name. Okay, next thing is we have to submit it using a run script. So this run script here, I'm specifying that I want to use gold time, and I'm specifying my allocation. I happen to be at Brunel. I'm asking for 10 minutes of time. I'm asking for 4.2 gigabytes of RAM. So the maximum you can go to per node is 192 gigabytes divided by the number of processes. However, you'll notice that actually the amount of RAM available is slightly less than that division, which is about 4.8. You'll also notice that the programs generally take slightly more. So for example, in my case, I allocated the array n to be about basically 4 gigabytes. What you'll find is the program will use more than 4 gigabytes, just because there's obviously some overhead from the actual program itself. So the advice is to be slightly conservative in what you ask for. If you don't, you'll find that the allocation is spread over multiple nodes, or your job will crash. So I found about 4.2 is about reasonable. Giving it a name memtest, asking for 40 MPI threads, and specifying the work directory, which is just memtest under my home directory. I'm then using the user bin time function in a verbose mode, so give me my output, and that timing is being applied to GE run of a.out, which is the compiled example I just showed you. Now, the one thing to bear in mind is that there is a default time function, but the one you want is under user bin time. So just be very aware that there are actually two different time functions on Linux. Okay, so with that in mind, we can then basically qsub that run script, and if we do that, we get the job running on there. Now what we can do is nodes for a job, and we take the job number here, and it gives us information on that. So it will tell us now that it's using 88% of the memory, and the loading is about 30%. Now, as I note here, because you're using hyperthreading, then actually the best we can get for 50%. But this is 88% of the job. That was using basically 4 gigabytes. And notice it's using just a single node. So it's worth looking at this kind of information. This will give you an idea of basically how efficient in terms of memory your job is. Now be very aware that if you've accidentally allocated too much memory, so in the example we give in the slides, if you go to 3.8, what you'll see is actually this then spreads over 2 separate nodes. So it comes back to the job allocation, but make sure you keep this below, certainly below 4.8. But I found, certainly for the different nodes, you might find they're slightly less than that again. Okay, so then we've got the output here. You see that there's various output files. We're looking for the one with the job number that's currently running. So that's 514989. 514989. So let's have a look at this. And you can see it's told us the host file, so the nodes that's been allocated on. We can also look at the error file and the standard output for the job. The other thing you can do is you can do qsat job and then the job number to get more information on this. And you can see CPU usage, you get more information. You see requested 4.2 gigabytes here.